Number 6 is the question. Okay. Now, facing in your hands here should be your Exam 3 handout, right? So it should be the only thing that you should be holding and taking a look at for this stuff. Okay. 250 mils of 0.85 molar HNO2 is titrated with 1.2 molar KOH. What conjugate acid or base is formed at the equivalence point, and what is its concentration? So, Brittany, what type of question is this? Is this a buffer question? I see an acid and a base in there, and use Henderson-Hasselbalch. What kind of question is this? Is this a buffer question? Or an ice question, you write the Ka reaction and then do ice, get the pH. The equivalence point calculation. All right, now what was the trick to doing this? Right? Oh, okay. That's in there. What is its concentration at the equivalence point? What Brittany said we're going to need sooner. Well, later rather than sooner. Moles over total liters. We're going to need that. Okay. So what, specifically, what conjugate acid or base is being formed? I don't have any sheets. I'm blank. NO2 negative. NO2. Does everyone catch that and why Brad says that? Sorry. NO2 negative. Now there's a trick to this that sometimes helps, sometimes doesn't. This thing. What if this was some complicated thing like methylamine or something? We've had that. You don't even know what the heck that compound is, right? But there's a trick to this. If you titrate with a base, you get a base. If you titrate with an acid, you get a acid. So we're titrating with a base, so we're going to get a base. So that means whatever, right, the chemical equilibrium is coming up, you're titrating with a base, so you're going to get a base. That means you better write a K what reaction right here. We're kind of jumping ahead, but it really helps for part A. You're going to write a K what? KB. You have to. Okay? This is going to be a KB reaction. Okay. So if you start thinking of it that way, what Brad is saying might be easier to figure out. You have to figure out what conjugate base is there. And that's what he did. He looked at what was being titrated here, and he just ripped off an H+. Ripped off the acidic hydrogen. And if you forgot to write the little negative, well, I guess you'll get a point taken off because they want to know what the base is, but it's not going to affect any calculations, really. Okay. And what is concentration? Brittany really helped us out with that. Here it is. Okay, keep going over there. Monte, how are you going to mess with this? So Brad gave us this part. We want to find the concentration of NO2 minus. And Brittany said that's going to be the moles all over the total liters. So can you give me one of these here? Either the moles or the total liters, or how to get it? Okay, the total liters part, you said that's going to be the 0.250. And all right. How do you get the other one? But you know there's going to be something. That other one is coming from what? That KOH that you're dumping in there, right? So how do you get that? Israel, how do you get that number? That number right here that Vante is saying, I don't know, I forget. How do we get that number? Can anyone help them out? Well, we're going to need a mole bridge. Definitely we're going to need a mole bridge. Where can we start, though? Let's not get the mole bridge until we actually need it. Have the calculation demand it. Where could you start in getting this number of liters? You could start with the 250 mLs. It's the most logical place to start, I think. You could start with 0.85 big M HNO2, and big M is what over what? Moles over liters. The only problem with starting with anything other than the 250, if you want to start anywhere else, it's fine, but you don't know if you should start with the moles on top or the moles on bottom, right? Maybe you should be writing liters per mole instead of moles per liter, right? And the calculations tell you what to flip. Well, if you start with the 250 milliliters, there's nothing to flip. You just start there, right? You can't really screw up. That's why I suggest starting there. Okay. I guess, let me back up. The only other logical place to start, I think, might as well tell you this, because it makes logical sense to me. You're after liters of KOH, right? You could start here. Liters all over 1.2 moles of KOH. That's a logical place to start because liters is on top. And you know those are the units you need. So you can start there too. You just got to cancel the moles of KOH, keep canceling until all you end up with is liters. So that would work too. But I think this is how we started out in class. Okay, that's how we started out. Okay, so if that's where you want to start out, I think it's a good place. That's how we've been doing it this whole time. What would be the next step? Anybody? Get it into liters. Let's make one big long calculation instead of breaking this up. Okay. Then what? 0.85 moles. All right. Now why not the other guy? 0.5 moles of HNO2. Ah, thanks. 0.85 moles of HNO2. My goodness. Newt all over liter. Now, see what they're, Glorianne or someone picked it? She picked this one. Why didn't she pick the KOH big M? Why not? They both have moles and liters in them. This is whose solution, that 250? That's the HNO2. That's all she, you have to do the HNO2. Oh, we shouldn't be this lazy, but we are. We should have wrote 250 milliliters of HNO2 solution. In a liter of HNO2 solution, there's 1,000 mils of HNO2 solution, right? And then 0.5 moles of NO2 in a liter of, that should be HNO2. All right, 0.5 moles of HNO2 in a liter of HNO2. Right. Okay. Now we're ready for a bridge. They're always one-to-one. Yeah, they're always one-to-one. All we're messing with is monoprotic stuff.
Is there ever a one to titration?
Oh, analytical chemistry. They'll be more complex.
So we can always skip that step for the sake of this class?
Well, if you skip it, your units are going to be messed up. Right? Because we want 1 mole of what up on top? KOH. See, if you skip this, your units are going to be messed up. Numerically, you won't be, but because now if you put it in, it should be clear what the last guy is going to be. What are you going to put in there, Bianca? What are you going to put in there? Yeah, there it is. Liters. She's looking right here. Liters all over the 1.2 moles of KOH. And you can just write OH if you want. Okay, and then we'll have it. That's how many liters of KOH we had to add. And that number, whatever we get, we'll put in right there. Okay. Okay, so we can get the total liters. Let's get that number there. 250 divided by 1,000 times 0.85 divided by 1.2, about 0.177 or so. Okay, so there's our total volume. We need to get the moles. Let's see if someone's got an idea how to get the moles now. The moles of what? The moles of the NO2 minus. Oh, Jesus, how are you going to get that? The moles of the NO2 minus. I see where you're going. That might work. But this to me is kind of like the buffer problem. If you're careful and you did this, you showed all your nice little work here, use this. Now, where you're going somewhere, it might be right. But it just dawned on me, our answer might be in here. If we just stopped where would we have our answer?
Right after the H.
Stop right there.
We're making the assumption here that it's titrated.
Yeah, well, yeah, otherwise, you're always assuming the dude did it right. All right? Yeah, if they stop too early, add too much, then, all right? Yeah, because if you stop here, you have moles of HNO2. Really, we need a new mole bridge, 1 mole of HNO2 for every 1 mole of NO2. But you really could just stop right there, because all of the conjugate acid is converted to conjugate base. We were talking about Jesus might have worked there, but I was just thinking, heck, just stop here. You don't think it would work? I think everything's chemically equivalent. That's why it might have worked. All right, stop here. Okay, so we have, I need a calculator. 250, it's 0.212. Thanks, Brittany, 0.212. Moles of HNO2, but that means you add 0.212, you're going to get 0.212 moles of NO2. So our concentration of this thing, finally we're ready for this, is going to be 0.212 moles all over 0.25 plus 0.177 liters. Comes up to 0.49 for the whole answer. Anybody else get 0.49? Kelly, you get 0.4? Okay. 0.49 is the final answer. Okay. 0.49. The how do you get the moles or the total liters? Okay. There's another way that we can get the moles that we did in class. This is how we did it. I think this is how we did it in class. We just set up the big what equation? The big M equation. You could do that too, right? Using this information, set up the big M equation. Maybe you're more used to doing it that way. That's how we did it in class. And you'd have 0.85 has to equal moles all over 0.25 liters. We did it that way too. And notice how it's the exact same calculation. It's the exact same calculation. So either way would work. Okay. Write the chemical equilibrium occurring at the equivalence point. Now we said earlier, Marcus, that's supposed to be a KB reaction. So I'll give you the arrow. What's the KB reaction going to be? NO2 minus and some water gives OH minus and the conjugate acid. Perfect. Find Ka or Kb for the chemical equilibrium. Okay, Kelly, how do How'd you do that one? You want KB? Well, I guess. KB equals, what'd you do? KW over the KA. So we have to look up Ka, Monica, for some acid there. Let's see, now Kw is 1 times 10 to the negative 14. And Monica, you're going to look up Ka for which acid? HNO2, and it is 4.5 times 10 to the negative 4. Okay, thank you. And somebody's got a calculator here. Crystal, way in the back, did you calculate this? 2.2 times 10 to the negative 11. Crystal got. Anyone second that? Okay, yeah. Okay. All right. Okay. So that was number 6. What number would you like to do next? Number 5. Okay, number 5. A buffer is prepared by adding 300 mils of 0.82 molar HClO and 250 mils of 0.75 molar NaClO. And they give us the Ka. What is the pH of the buffer solution? Okay. Where do you start? Where do you start? Desiree, where do you start? The negative log of what? 3.5 times 10. This is where Desiree started. Why is that a good place to start? Because you need it. Yeah, exactly. You need it. You need it for whose equation? Yeah, that buffer equation. Okay. Now, pH equal. You copy it. But do you want to copy it verbatim, or do you want to modify it how we did it in class? Verbatim? I think it's easier if you modify it. Yeah. The reason why I think it's easier if you modify it is, where's the one we just did? This guy. See, because you can reuse calculations. We reuse this part. And if you, not to say we're going to reuse the same part, the point is we can, to answer part B, we can use part A if we're first careful and we show all of our work. Okay? If you do concentration, you just have to divide by volume is all. Okay. Now, Desiree already gave us this part. 3.5 times 10 to the negative 8. And we need a log of it. I got about 7.456. And I'm going to write a bunch of digits, otherwise things get kind of funky. Okay. So right now we have 7.456 for that. Okay. Pamela. Moles of base or moles of acid? Which one you want to shoot for here? How are you going to get it? Okay, moles of base. How are you going to get this? We can use the big M equation. You can do that. Or you can realize big M is moles over liters. It's kind of faster. Realize big M is moles over liters. Just multiply big M by what, and you're going to have moles. Yeah, the liter is 0.25. But either way works. Okay. But she wants to do the big M equation. That works. Of the Na one or the HClO one? The Na, right? Because here's our base. Remember, we don't look at the alkali metals. There's our conjugate base, ClO negative. Okay. So So we're going to have 0.75 is going to be the moles all over 0.25 liters. See? So to get the moles, you pretty much multiply big N times liters. And we'll get the moles, the base. .25 times 0.75, about 0.1875. Get the moles of the acid. Anybody get that answer? 0.246. Brad got 0.246. Anybody else get that? All right, good. So same exact way. Now we can set up our whole equation. pH is 7.456 plus the log of 0.1875 all over 0.246. Okay. Jalen, did you get an answer yet? You're still plugging it in there. Yeah, final answer. 7.3? Do you have any more digits than that? 7.30? 7.34. All right. Well, somewhere around there, right? Okay, I'm just trying to get a lot of digits because these numbers, these pH for the second part, they only change a little bit. So that's why I'm carrying a lot of digits here. Okay. Is everyone comfortable with that first part? Okay. Now we have this buffer solution. It's a mixture of a conjugate acid and the conjugate base. We're going to add, what type of acid is that? HCl. Strong acid. pH should drop like a rock, but buffers don't let that happen. Buffers have an acid in them to react with bases, yes. All right? If a base is dumped in a buffer, an acid is going to react with it. If an acid is dumped in a buffer, there's a base there to react with it. Right? So it should relatively stay the same pH. What base is there to react with HCl? What base is there to react with HCl? Yeah, the CLO is the base, CLO negative. That's our base. You could say NaClO, you're not wrong. That's our conjugate base. But I think it sounds better and looks better just to say CLO negative is our conjugate base. That's what's going to react with that HCl. Every drop of HCl you add, CLO negative is going to react with it. Okay. But it's going to get converted into what? CLO negative is going to react with HCl and get converted to an acid. What acid? HClO. Yeah, it's conjugate acid. Now, is HClO a strong acid? No, it's weak. So you're generating a weak acid. Okay, well the pH is going to get more acidic, but not near as bad as if you add a strong acid. You're converting a strong acid into a weak acid is really all you're doing. So the pH will get lower, but not by very much. Okay. So here's where I'm saying, if you're nice and neat with your work, you take this, you copy it down here, right? Just have to see what's going to change. It's a buffer problem. Okay, so what's the trick to this? Yeah, I gotta use those. Okay.
Well, yeah, but because you have to do the subtracting and the adding.
Okay, the subtracting and the adding. We're going to subtract on the top, or we're going to subtract on the bottom? We're going to subtract on the top because the base is reacting, right? That base number has to go down, so you have to put a minus there. The acid is forming, so you better put a plus. Okay, that's the first thing. that logic has to tell you. Then you have to think about, okay, what is that number? Is that number going to be the same both here and here?
Yes.
Yes, it's going to be the same. So we'll figure out where to get that number. Then the other complication is, did we add it to the whole buffer? If we did, don't do anything else, right? But if you didn't, you better reduce those moles of base and moles of acid that you started out with. Okay. Well, let's figure out what this number is first. What is this number that we're adding and subtracting? What do you use? We've got a bunch of stuff here. You can use the big M equation, you bet, because it has to be moles. But which set of data do you use? I mean, you've got a bunch of them here. Exactly. It's the moles of the strong acid or strong base that you added. That's what you're changing by. Right? Don't let it confuse you. You've got a bunch of milliliters, and there's a bunch of sets of data you could write big M for. But think about what it's changing by. It's changing by, ooh, I added this HCl. Something better react with it. So how much is going to react with it? Well, it just depends how much you added. So that's what we'll figure out. Big M is going to be 0.35 moles all over 0.025. So pretty much just multiply big M by liters, and you always get it. But 8.75 times 10 to the negative 3. So that number's going to go here. It's going to go there. We're done if you change this question to what? What would be the English? You get a final answer. If you reworded this question to say what? Or cross out what? Yeah. What would be the pH of the buffer? Just cross out the 100 mils. What would be the pH of the buffer if you added 25 mils of 0.35 molar HCl? That means you added to the whole buffer, the whole big beaker of stuff. You'd be done. But you didn't. You added it to a fraction. You have to multiply those numbers times the fraction. Did you use half? Did you use a third? Did you use an eighth? Did you use 100th? How do you figure out that fraction? 100 divided by 550. Whatever you added divided by the total. Right? Okay. Well, let's change the 100 to a total. The total is how much? How much do you have? How much buffer do you have to work with?
You have 0.55 liters.
You have 250 milliliters plus 300 milliliters. You see where Brad's getting the 0.55 liters? Right? So your total volume is 550 milliliters. So if they would have said, use 550 milliliters of the buffer, well, that's everything you got. These would just be ones. But if it was, what's half of 550? 275? If they would have said 275, right, then you would have had to put your fraction is 275 over the total. That'd be a half. But what fraction are you calculating? Not 275, but 100. Yeah, every single time. Have the total in the denominator and the fraction that you're taking in the top. And that'd be the fraction that you're using. 100 over 550. What is that? 5 point. It has to be less than 1.
Oh, yeah.
0.18. 0.18. So this should be, I got to write bigger here, 0.18. And this one is 0.18. Okay. So now we've got a lot of stuff to calculate here. We'll do it. Oh, my goodness. I totally screwed up here. 0.18. Okay, did you get like 7.303? Yeah, it just depends on. With logarithm, for you to get the exact same answer as me, we have to be carrying the exact same number of digits. So that's why you may not get exactly 7.30, but it should be somewhat close to that.
Now remember
Right.
we were working it in your class and it's 7.29, and we went back and we reworked it and it came out to 7.13.
No.
And the answer before was 7.1.
Okay.
Like
So what you need to be careful of is when you hit equals and that sort of thing, right? Like to get this, 0.18 times 0.1875 minus 8.75 times 10 to the negative 3, hit equals, right? Because if you hit divide by, it's only going to divide that 8.75 to the negative 3 by 0.18. So either use parentheses or break it into two parts, okay? So either use parentheses in your calculator or break it into two parts, okay? But the real hint for me for all this is that you get a number that's really close to the pH of the buffer before you add anything. You should get a number really close to it, because that's the whole point of a buffer. The pH isn't going to change much. So the pH didn't change much, but it did get a little more acidic. Okay? So whether you got 7.28 or 7.29 or 7.31, the point is it got a little more acidic. And it changes a little bit. And we'll be much more careful in more advanced courses, but the point is these are the general calculations.
I just skipped this step. It's even this part into this section.
Okay.
It's the same. Okay, that's what I thought.
Okay?
I did just say that was 2 numbers. It's still about 7 Like it's
I can try it again.
That's what I got. I got 7.29.
Yeah, and then I got 7.29. And then when we worked it in your office, based on everything that we got, I brought it down to 7.13. It's like 6 or 7 times working this problem. I told everything from 7.1 to 7.29.
Oh, that's point. I switched the numbers. What is that called when you transpose numbers? I'm not dyslexic. 0.05.
Upside down.
I got 0.053, not 0.035. Yeah, I got 0.053. Okay. Log. .13.
Well, how are you getting that now?
Make sure you get 0.025 and 0.053, otherwise why continue? Right? How is there a different way? How is there a different way? You have to, no matter how you do this question, you have to end up with 7.456 plus the log of 0.025 over 0.053. It doesn't matter how you, there's no, you don't have, that's,
I feel confident with this
take 0.18 times 0.246 plus 8.75 times 10 to the -3. Okay. Bless you.
I didn't do it right. I just forgot to do this part. We never worked one out, so.
Well, now we did.
Can we do number 8 now?
Number 8? Okay. Number 8. 7, 8. What is the solubility of lead fluoride in 0.05 molar lead nitrate? And there's the KSP. Solubility is the...
Ice.
Solubility is the... Yeah, but it's the what in ice? X.
Why did you so like this?
Because I'm strangling Gloriana's neck. All right. So we're supposed to find the X in ice. That means you got to have a reaction. What reaction? It's always in what general way? The solid going to its ions. Every single time. The solid going to its ions. And the solid is PbF2.
Okay, so when do you do the little crisscrossing of the things, like instead of like no.
Let's finish this. And the ions are Pb2 plus and 2F minuses. Good. Okay. What should you do right away so you don't screw up? You can write little AQs, yeah, but do what? Dashes where? On the solid all the way down. Right? Wait, let's finish this. Okay. Is there anything there initially?
Yes.
Yes. There. Otherwise, we usually just put dashes or zeros. But there's something there initially. What is it and where? Yeah, this thing. In fact, I'm used to telling you to cross out sodium ions and potassium ions. Well, there's one anion that I told you to cross out too. It never forms a precipitate. NO3. It never can form precipitate. So you really don't have this guy here. You have 0.05 lead. Do we have any fluoride there initially? No. They could have. They could have said 0.2 molar NaF. Well, then you'd have to put a 0.2 under the fluoride. But they didn't. Okay. Change row minus X and... Oh, and they're not negative X. They're plus X's, aren't they? Thank you. So we're forming them. And 2X. 0.05 plus X and 2X. Okay, now how do we get numbers for this X? We have to set up a what now? The KSP. And I think you shouldn't skip this step. Write the darn bracket things out. Otherwise, it's just silly mistakes. Right? Write the lead and the fluoride squared. Otherwise, you just end up silly mistakes. That takes 1 second. Then you substitute everything in, the equilibrium concentrations. You get it from the E row. That's where all of our answers are. So we'd have 0.05 plus X and 2X squared. Okay. Oh, we got to look up the number for KSP. Oh, they told us. 2.7 times 10 to the -8. Ooh, I like that number. So we can say what is approximately 2.7 times 10 to the negative 8? How does it get simplified? Because of that negative 8 exponent. Yeah, so it would look like what? 0.05 times... Yeah, exactly. Nothing else changes, right? 0.05 times 2x squared. So 2x squared is, well, 2x quantity squared is really what? 4x squared times 0.05, so... And then divide it by, solve for your x squared, so then you can finally take square root at the end to get your x. Point 2. So I have to take the square root of 1.35 times 10 to the negative 7. You get about 3.67 times 10 to the negative 4. Okay. Ooh, nice. Why can we quit? It just asks for solubility. Usually they ask for what units? Grams per liter, right? But they didn't. So you can. There's nothing stopping you converting this to grams per liter. But you can just quit here, but you're still going to lose points because you need units. Moles per liter. Big M. This is always moles per liter. Or big M. X is always. Like those ice tables, those are concentrations. Those are moles per liter. Big M. All right, look at those are brackets. Okay, let's make a part. Okay, part B, in grams per liter. Right. So here's part B. They want it in grams per liter. Right. They want the answer in grams per liter. We need the molar mass of what? PbF2. This is your solid. All right, we need the molar mass of PbF2. And a mole of PbF2. I have so many grams of PbF2. My moles cancel, and I end up in grams per liter. So what's the molar mass of PbF2? 245? Okay. And then final answer of 0.089. Victoria, you get 0.089? Wow, she's like, that's helping you.
At least she's honest.
Anybody else get 0.089? Yeah? Okay. Okay, 0.09. Okay, now Brittany is jumping at the bit here. What is your question?
When do you switch it? Like, why wouldn't it have been PB and O3? When I remember talking about it, like we had to switch the cation and the anion and like put them together, like from the two different stations.
Okay, the question that she's thinking about, that Brittany has a game plan, but she doesn't know what the question is. Let's see if you can remember the game plan. The game plan is where they gave you these two solutions, and they said, ooh, will a precipitate occur? Do you remember this? Will a precipitate occur? This is what she's been itching to do, but she couldn't do it on this question. She wanted to take the cation in one of those solutions, give it with the anion, right? And the cation with the other solution, give it with the anion, right? What is that? That question is, I bet you it's in our review. Let's see one of those. Oh, we don't have one. But yeah, I'd have to write it. I could write it.
No, that's okay. There wasn't any in the homework either, so.
Well, it'll be in the review session. Let me write a question here quick. I need to get bigger so you can read this. Okay, we're adding 250 milliliters of 0.23 molar sodium. Where's my solubility table here? Well, you're seeing so sodium fluoride and let's do okay, this is a question that Brittany was wondering about. You have a couple minutes. 250 mils of 0.23 molar NaF and 223 mils of 0.44 molar calcium nitrate are mixed. Forgot the are mixed part, right? Will a precipitate form? Okay. You saw it being created before your eyes. All right. Now you have this chart, this handout staring at you for this exam. Will a precipitate form? What was the game plan that Brittany was talking about? You take the cation here, because you know this can't be a precipitate, it has big M on it. So sodium fluoride and calcium nitrate cannot be precipitates because they're solutions. See the big M, they're dissolved already. Okay, so that means it has to be either sodium nitrate or calcium fluoride has to be a precipitate. If you're not sure, hell, just look at the KSP table. One of those has to be in there. But if you remember what we talked about in class, you know which one is in the table. Which one is it? It's the CAF one, right? It's the calcium fluoride. So you can find it in the table, or just write it out. Write out the KSP reaction for calcium fluoride. All right? But are we interested in doing solubility? Ooh, find X. No. We want to know if a precipitate will form or not. So you calculate a pretend KSP. We didn't call it KSP, we called it QC. You calculate a QC. And if it's bigger than the KSP, a precipitate forms. That's all. That's the question. That's the question that's going through your head.